Greetings, cosmic explorers, and welcome to Earth with Nature, a serene corner of the universe where we ponder life's deepest mysteries. Tonight, let's dive right into a profound question. Is the universe flat, curved, or something stranger? Before we embark, if this journey sparks wonder in you, please take a moment to like this video and subscribe to Earth with Nature. Also, drop a comment to share where you're tuning in from and what time it is there. Now, settle in, dim the lights, and let's explore the shape of reality itself, a puzzle that stretches beyond our wildest imagination. Imagine yourself floating in the boundless void of space, surrounded by a tapestry of stars and galaxies, with no edges or borders in sight. What shape does this vastness hold? Is the universe a flat, endless plane like a cosmic sheet of paper, a curved sphere that loops back on itself, or something far stranger, folding in ways we can't yet grasp? This isn't just a whimsical thought. It's a fundamental question in cosmology, tied to the very fabric of space-time as described by Einstein's theory of relativity. Picture light from distant galaxies traveling billions of years to reach us, bending or stretching along paths dictated by the universe's geometry. Astronomy and planetary science facts guide us here, using tools like the Cosmic Microwave Background (CMB), the faint glow of the Big Bang's aftermath, to measure subtle clues. Pause for a moment. How does it feel to consider that the space holding every star, every planet, and you right now might have a hidden form? Let's delve into the science behind this cosmic riddle, uncovering how we probe the shape of everything. To unravel whether the universe is flat, curved, or something stranger, scientists turn to an array of ingenious methods and cutting-edge technology. The CMB, captured by satellites like NASA's Planck mission launched in 2009, acts as a cosmic ruler, its tiny temperature fluctuations revealing the geometry of space just 380,000 years after the Big Bang. If the universe is flat, light paths remain straight, and triangles drawn across vast distances sum to 180 degrees, as Euclid taught us. A positively curved, closed universe like a sphere would see light converge, with triangle angles exceeding 180 degrees, while a negatively curved open universe shaped like a saddle would show angles less than 180 degrees. Gravitational lensing, where massive objects bend light, offers another clue, as seen in observations by the Hubble Space Telescope, mapping how space warps around galaxy clusters. Then there's the rate of cosmic expansion, measured via supernovae and redshift data, hinting at density. Too much matter curves space inward, too little opens it outward, and just right suggests flatness. Recent data, like the 2018 Planck results, pegs the universe as flat within a 0.2% margin of error. Yet questions linger. Reflect for a second. What if flatness is just an illusion on our scale? Could there be stranger topologies? Space folding like a torus, hidden from view? Let's linger on these possibilities as we explore the three grand geometries shaping this debate. As we drift deeper into cosmic wonder, let's meet the three great possibilities for the universe's shape: flat, closed, and open. A flat universe, balanced at critical density, expands forever at a slowing pace, its parallel lines never meeting, a familiar, orderly realm echoing schoolroom geometry. A closed universe, denser and curved inward like a sphere, loops light and paths back on themselves, potentially collapsing in a big crunch billions of years hence, a finite yet boundless space that evokes both awe and a quiet unease. An open universe, less dense and saddle-shaped, stretches endlessly, with galaxies racing apart faster over time, a lonely expanse where parallel lines diverge. Each geometry, rooted in planetary science facts, ties to the universe's fate. Will it endure, collapse, or fade into cold infinity? Imagine yourself as a photon, traveling straight yet guided by unseen curves, carrying the story of space's form across eons. How does it stir you to know our reality's shape dictates its destiny? This isn't just science. It's a mirror to our own fleeting existence, urging us to ponder our place in an ever-shifting cosmos. Let's hold this thought as we consider stranger possibilities beyond mere curvature, where the universe's very structure might defy intuition. Now, let's venture into the realm of the truly strange, where the universe's shape might transcend simple curvature into exotic topologies. What if space isn't just flat or curved but connected in bizarre ways, like a donut-shaped torus where traveling straight loops you back through unseen folds? Such ideas, explored in theoretical cosmology, suggest that light could return to its starting point without curvature, a mind-bending twist detected perhaps by repeating patterns in the CMB, though no conclusive evidence exists yet. Projects like the upcoming Simons Observatory aim to refine these measurements, while concepts like holography propose our 3D reality might be a projection of a 2D boundary, a notion born from string theory and black hole studies. Consider the emotional weight of this. If the universe is stranger than we imagine, does it make Earth feel more precious, a tiny anchor in an incomprehensible design? Future missions, such as the European Space Agency's Euclid satellite, launched in 2023, will map billions of galaxies to test these theories, potentially rewriting our cosmic story. Pause and wonder. How would discovering a looped or holographic universe change your view of reality? As we marvel at these frontiers of exoplanet mysteries and beyond, let's remember that each clue ties back to our own existence, grounding us even as it expands our horizons. As our exploration of the universe's shape, flat, curved, or something stranger, nears its end, let's pause under the vast cosmic canopy, feeling the weight of questions yet unanswered. We've journeyed through the science of cosmic geometry, marveled at planetary science facts, and ventured into the wild possibilities of topologies beyond imagination. I hope this has ignited a spark of cosmic wonder within you, a quiet awe for the reality we inhabit. Before we part, I'd love to hear your thoughts. Comment below with your reflections on the universe's shape, or just share where you're listening from and the time there. If this journey touched you, please like this video and subscribe to Earth with Nature for more thoughtful dives into the mysteries of existence. Your support helps grow this sanctuary of curiosity. Until next time, keep gazing at the stars, wondering about the shape that holds them, and cherishing the tiny world we call home. Good night, friends, and may your dreams echo with the universe's cosmic journey into the shape of the universe. Let's dive deeper into the concept of flatness and what it truly means in the context of cosmology. A flat universe, as suggested by the latest measurements from the Planck mission, implies a precise balance of matter, energy, and dark energy, aligning with a critical density that neither collapses nor expands infinitely without bound. This flatness, measured to within a 0.2% margin of error, is not just a geometric trait but a profound clue about the early universe's conditions during the Big Bang. According to the theory of cosmic inflation, a rapid expansion just fractions of a second after the Big Bang, any initial curvature would have been stretched out to near-perfect flatness, much like a balloon's surface appears flatter as it inflates. This is supported by observable data. The CMB's temperature fluctuations form patterns consistent with Euclidean geometry, where the largest hot and cold spots span about 1 degree across the sky, a direct signature of flatness. Moreover, flatness correlates with the universe's expansion rate, measured through type Ia supernovae, which act as standard candles due to their consistent brightness, revealing a cosmos neither accelerating nor decelerating too drastically until dark energy's influence kicked in about 5 billion years ago. Consider the precision required for this balance. Had the density differed by even 1 part in a trillion at the universe's birth, we'd live in a radically different reality. This fine-tuning raises philosophical questions. Is flatness a cosmic accident, or does it hint at deeper laws, perhaps tied to a multiverse where countless universes exist with varying shapes? As we ponder this, let's remember that flatness isn't just a number. It shapes the very paths of light and matter, including the signals we use to study distant galaxies, reminding us how interconnected geometry is with our understanding of existence. Reflect on this. How does knowing our universe might be balanced so perfectly alter your sense of its stability or fragility? This exploration of flatness isn't merely academic. It's a window into the initial conditions that birthed everything we know, urging us to keep questioning the fundamentals of space-time itself. Now, let's shift our gaze to the implications of a closed universe, a geometry where space curves back on itself like the surface of a sphere, containing a finite volume yet lacking boundaries. In such a cosmos, if you traveled far enough in one direction, you'd eventually return to your starting point, much like circumnavigating Earth. Except this happens in 3 dimensions, a concept that challenges our intuitive sense of endless. Scientifically, a closed universe would arise if the density of matter and energy exceeded the critical threshold, causing gravity to eventually halt cosmic expansion and trigger a collapse, often termed the Big Crunch. Observations of galaxy clusters and gravitational lensing, studied through telescopes like the James Webb Space Telescope launched in 2021, help estimate this density by mapping how mass distorts light paths, while CMB data probes early universe conditions for signs of positive curvature. Current evidence leans against this model, as the measured density parameter omega hovers near 1.0, indicating flatness rather than the greater than 1 value needed for closure. Specifically, Planck 2018 data suggests omega is 1.000 plus or minus 0.002. Yet, a closed universe isn't ruled out entirely. Small undetected curvatures could still exist beyond our observational horizon, which spans about 46 billion light-years despite the universe's 13.8 billion year age, thanks to expansion. Imagine the implications. A finite cosmos might mean a finite number of stars and galaxies, a contained reality that could one day contract, erasing all we know in a fiery reversal of creation. Historically, this idea echoes ancient cosmologies, like those of the Greeks, who envisioned a bounded cosmos, blending science with existential dread. Pause and think. If the universe were closed, would it make you feel trapped or strangely comforted by its limits? This geometry also affects practical astronomy. Light bending back could create duplicate images of distant objects, a phenomenon still under investigation. As we explore this possibility, let's hold on to the fact that even a closed universe, per Einstein's general relativity, remains boundless in experience, pushing us to rethink what finite truly means in the grand tapestry of spacetime. Turning now to the open universe model, we encounter a geometry as unsettling as it is expansive, where space curves negatively like a saddle or hyperbolic surface, stretching infinitely without closure. In this scenario, the density of matter and energy falls below the critical value, omega less than 1, allowing gravity to lose its battle against expansion, causing galaxies to drift apart forever at an ever-increasing rate, leading to a cold, dark future often called the Big Freeze. This shape distorts light paths so that parallel lines diverge and the angles of a triangle sum to less than 180 degrees. A stark departure from everyday geometry. Observations supporting this model would show specific patterns in the CMB, with larger scale fluctuations than in a flat universe, though current data, including the 2018 Planck results, show no significant deviation from flatness, placing omega within a tight range of 1.000. Additionally, studies of baryon acoustic oscillations, ripples in galaxy distribution from the early universe, act as a cosmic yardstick, reinforcing the flat or near-flat conclusion, as their measured scale matches predictions for a non-curved cosmos. Still, an open universe remains a theoretical possibility, especially if dark energy behaves differently over cosmic timescales, a topic under study via missions like the Dark Energy Spectroscopic Instrument, DESI, which began mapping galaxies in 2021. Picture this future. Stars burn out, black holes evaporate over trillions of years, and the universe becomes a sparse void, a fate dictated by its open shape. This evokes a profound loneliness, yet it also highlights the transient beauty of now, our era of stars and life. Reflect for a moment. Does an endlessly expanding, open universe make our current connections feel more fleeting or more vital? From an educational standpoint, understanding this geometry teaches us about density's role in cosmology, linking fundamental physics to the universe's ultimate destiny. And it underscores why precise measurements like those of cosmic expansion via Hubble's constant, currently estimated at 67.4 plus or minus 0.5 kilometers per second per mpc by Planck, are crucial. As we linger on this open possibility, let's appreciate how it challenges us to value the present cosmic moment amidst an uncertain future. Let's now explore the mind-bending concept of cosmic topology, a field that asks whether the universe's shape involves hidden connections beyond simple curvature, potentially looping or folding in ways we can't directly see. Unlike the geometries of flat, closed, or open, topology considers if space might be multiply connected. Imagine a torus, donut shape, where traveling in a straight line brings you back through a different path, not due to curvature but due to the space's intrinsic structure. This idea, rooted in mathematical frameworks like differential geometry, predicts that light from a single source could reach us via multiple paths, creating detectable repeating patterns or ghost images in the CMB or galaxy distributions. Despite extensive searches, such as those using data from the Wilkinson Microwave Anisotropy Probe, WMAP, from 2001 to 2010, no conclusive evidence for non-trivial topology has been found. The observable universe appears simply connected within our detection limits, spanning roughly 93 billion light-years in diameter. However, if the universe's true scale exceeds our observable horizon, these loops could exist beyond our sight, a hypothesis testable only indirectly through statistical anomalies in cosmic data. Upcoming surveys, like those from the Vera C. Rubin Observatory starting operations in 2025, aim to map billions of galaxies for subtle topological signatures. Contemplate this. If space loops, it could mean reality is more intricate than any map we draw, challenging our very notion of distance. Educationally, topology bridges pure mathematics with cosmology, showing how abstract concepts like manifolds apply to physical reality, and it ties to string theory's idea of extra dimensions folded into tiny scales. Historically, thinkers like Poincaré speculated on such shapes in the early 20th century, long before observational tools existed. Pause and wonder. How would discovering a toroidal universe shift your perception of travel or infinity? As we delve into this, let's recognize that topology doesn't just question shape. It questions the fundamental nature of connectivity in the cosmos, urging us to think beyond three-dimensional intuition and embrace the unknown. Stepping further into speculative territory, let's consider the holographic principle, a radical idea suggesting that our three-dimensional universe might be a projection of information encoded on a two-dimensional boundary, much like a hologram projects depth from a flat surface. Originating from black hole physics in the 1990s, particularly through the work of physicists like Juan Meldacena and Leonard Susskind, this principle posits that the universe's volume is described by laws operating on its surface, potentially at the cosmic horizon. This ties to string theory and the AD/CFT correspondence, a mathematical framework showing a gravitational 3D space can equate to a non-gravitational 2D theory, offering a way to reconcile quantum mechanics with general relativity. While there's no direct evidence, our observations align with a 3D reality. Subtle hints might emerge in CMB fluctuations or quantum entanglement patterns, areas under scrutiny by theoretical cosmologists. Experiments like those at the Large Hadron Collider, probing high-energy particle interactions since 2008, indirectly test string theory's foundations, though results remain inconclusive. Imagine the implications. If we're a hologram, does free will or physicality hold the same meaning, or are we shadows of a deeper code? Educationally, this concept teaches us about the interplay of information theory and physics, showing how entropy, disorder, in black holes relates to surface area, not volume, a fact derived from Stephen Hawking's work on black hole radiation in the 1970s. It also challenges students to rethink reality's dimensions, blending philosophy with science. Historically, this idea echoes Plato's allegory of the cave, where perceived reality is a mere shadow of truth. Reflect on this. Does the possibility of being a projection make the universe feel less tangible or more mysterious? As we explore, let's note that missions like the European Space Agency's Gaia, mapping stellar positions since 2013, build the 3D data we compare against such theories, grounding wild ideas in measurable fact. The holographic principle, while speculative, reminds us that the universe's shape, flat, curved, or stranger, might be an illusion hiding a profounder structure. Finally, let's synthesize our journey through cosmic geometries and topologies by examining how these shapes influence not just the universe's fate but also our technological and philosophical outlook. Whether flat, closed, open, toroidal, or holographic, each model affects predictions for cosmic expansion, observable phenomena, and even the search for extraterrestrial life. For instance, in a flat or open universe, signals from distant civilizations might fade into the expanding void, while a closed or looped space could amplify or repeat such signals, a factor considered by SETI programs using radio telescopes like the Allen Telescope Array, operational since 2007. Scientifically, understanding geometry refines our models of dark energy, which constitutes 68% of the universe's energy budget per Planck data, driving expansion and potentially altering curvature over eons. Philosophically, the shape question forces us to confront our scale. Earth, a mere speck 12,742 kilometers in diameter, floats in a cosmos whose form we barely grasp, humbling us yet fueling curiosity. Educationally, this topic integrates physics, geometry, and astronomy, teaching critical thinking through data analysis, e.g. CMB maps showing a flatness parameter of 0.001 curvature or less, and encouraging interdisciplinary study. Historically, from Euclid's flat postulates in 300 BCE to Einstein's curved spacetime in 1915, humanity's view of cosmic shape has evolved with observation, a trend continuing with tools like the upcoming Nancy Grace Roman Space Telescope, set for launch in 2027, to probe dark energy's effects on geometry. Pause and reflect. How does the uncertainty of the universe's shape inspire you to seek answers or accept mystery? Practically, This knowledge impacts space travel. Navigating a curved or looped cosmos would differ vastly from a flat one, a consideration for future missions beyond our solar system. As we close this chapter, let's carry forward a sense of wonder, recognizing that each measurement, each theory, brings us closer to decoding the universe's form, yet reminds us of the infinite questions still shimmering in the cosmic dark, urging us to keep exploring, learning, and marveling at the reality we inhabit. Diving deeper into the enigma of the universe's shape, let's explore the role of dark energy in shaping cosmic geometry, a topic at the forefront of modern cosmology and trending in scientific discussions due to its mysterious nature. Dark energy, comprising approximately 68% of the universe's total energy density as per the 2018 Planck mission data, is the driving force behind the accelerated expansion of the cosmos, first discovered in 1998 through observations of Type Ia supernovae by teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees, earning them the 2011 Nobel Prize in Physics. This acceleration, quantified by a Hubble constant of about 67.4 plus or minus 0.5 kilometers per second per mpc, Planck estimate, suggests that space itself is stretching faster over time, impacting whether the universe remains flat, becomes more open, or exhibits unexpected curvature. If dark energy's density remains constant, a property of the cosmological constant in Einstein's equations, it supports a flat or open geometry, pushing galaxies apart indefinitely. However, if it varies, as some models like quintessence propose, it could alter the cosmic fate, potentially leading to a collapse, closed geometry, or a big rip where expansion tears apart all structures. Current trending research, such as the Dark Energy Survey (DES), which concluded its 6-year run in 2019 mapping 300 million galaxies, constrains dark energy's equation of state to within 4% of a constant value, reinforcing flatness but leaving room for surprises. Moreover, the upcoming Nancy Grace Roman Space Telescope, set for launch in 2027, aims to refine this further by observing billions of galaxies to detect minute changes in expansion history, potentially revealing if dark energy's influence could curve space over cosmic timescales. Educationally, this highlights the interplay of observation and theory. Dark energy was inferred from redshift data, where light from distant objects stretches to longer wavelengths, indicating recession speeds proportional to distance, a cornerstone of Edwin Hubble's 1929 discovery of cosmic expansion. Philosophically, dark energy's unknown composition, possibly a vacuum energy or a new field, challenges us to rethink the stuff of reality, with ongoing experiments like the Xenon 1T detector searching for related dark matter particles, though no definitive results emerged by 2023. Reflect on this trending question. Could dark energy's evolution unveil a curvature we can't yet detect, reshaping our cosmic map? As social media buzzes with discussions on dark energy's role in popular science podcasts like Star Talk with Neil deGrasse Tyson, it's clear this mystery captivates both experts and the public, urging students to grasp concepts like energy density, measured in joules per cubic meter, and its geometric impact, while reminding us that 95% of the universe, dark energy and dark matter combined, remains unknown, a humbling fact driving 21st century astronomy. This exploration ties directly to planetary science facts, as understanding cosmic expansion influences models of galaxy formation, including our Milky Way, which houses over 100 billion stars and formed 13.6 billion years ago, shaped by the same forces we study today. Let's ponder how each new dataset, from DES to future missions, builds on this puzzle, pushing the boundaries of what we know about the universe's flatness or potential hidden curves, and inspiring the next generation of cosmologists to probe deeper into the accelerating void. Shifting focus to another trending frontier, let's examine the cosmic microwave background, CMB, in greater detail. A relic radiation from the Big Bang that serves as a snapshot of the universe at just 380,000 years old and a critical tool for determining its geometry. The CMB, discovered in 1965 by Arno Penzias and Robert Wilson, Nobel Prize 1978, is a uniform glow of microwave radiation at 2.725 Kelvin, permeating all of space, with tiny temperature fluctuations of about 1 part in 100,000 that encode the seeds of galaxies and the shape of spacetime itself. Satellites like NASA's Planck, operational from 2009 to 2013, mapped these fluctuations with unprecedented precision, revealing a power spectrum, essentially a graph of fluctuation sizes, that aligns with a flat universe, where the largest hot and cold spots subtend about 1 degree on the sky, matching Euclidean geometry predictions. If the universe were closed, these spots would appear larger, greater than 1 degree due to light convergence. If open, smaller, less than 1 degree due to divergence. A direct test of curvature rooted in basic trigonometry applied across billions of light years. Planck's 2018 final data release pegged the curvature parameter, omega sky, at -0.001 plus or -0.002, statistically consistent with zero, flatness, within a 0.2% margin, a result trending in cosmology news as it narrows the possible shapes to near-flat, though not definitively ruling out slight curvature beyond our precision limits. Educationally, this underscores the importance of statistical analysis in science. CMB data involves Fourier transforms to break down temperature patterns into angular scales, a technique students encounter in advanced physics and signal processing, showing how math unveils cosmic truths. Trending discussions on platforms like X often highlight the CMB's role in confirming the lambda CDM model, lambda for dark energy, CDM for cold dark matter, the standard framework of cosmology describing a flat, expanding universe, though anomalies like the axis of evil, a debated alignment in CMB patterns, fuel speculation of non-standard topologies or systematic errors, as discussed in 2023 papers on AR14. Historically, the CMB's discovery shifted cosmology from philosophy to empirical science, paralleling Galileo's telescope in impact, while current research, like the Simons Observatory in Chile, data collection began 2023, seeks even finer CMB polarization signals to test inflation and geometry further. Reflect on this viral topic. Could a tiny CMB anomaly hint at a universe stranger than flat, perhaps looped or multidimensional? This ties to planetary science by informing models of early universe conditions that led to star and planet formation, including Earth's own 4.5 billion year history. As CMB data constrains the baryon density, ordinary matter, to 4.9% of the total energy budget. As we delve into this, let's appreciate how the CMB, a whisper from creation, continues to trend as humanity's best window into the shape of everything, urging us to refine our tools and theories with each passing year. Now, let's turn to the buzzing topic of gravitational waves and their emerging role in probing the universe's geometry, a field that exploded into the spotlight with the first direct detection in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, earning Rainer Weiss, Barry Barish, and Kip Thorne the 2017 Nobel Prize. Gravitational waves are ripples in spacetime caused by massive accelerating objects, like merging black holes or neutron stars, predicted by Einstein's general relativity in 1916, and their propagation speed, equal to light's 299,792 kilometers per second, offers a unique test of cosmic curvature. In a flat universe, these waves travel along straight paths. In a curved one, their paths bend, potentially altering arrival times or signal strengths across vast distances, a phenomenon under study by LIGO and its European counterpart Virgo, which together have detected over 90 events by 2023. Trending research, highlighted in journals like Nature and discussed on science YouTube channels like PBS Spacetime, explores how a network of future detectors, such as the planned Laser Interferometer Space Antenna, LISA, set for launch in 2037, could map low-frequency waves from supermassive black hole mergers, providing a gravitational CMB, to cross-check geometric constraints from electromagnetic data. Current data shows no deviation from flatness, as wave signals match predictions for uncurved space. But precision limits mean subtle curvatures below 1% remain possible, aligning with Planck's CMB findings of omega near zero. Educationally, this introduces students to tensor mathematics and wave physics, as gravitational waves are described by metric perturbations in Einstein's field equations, a complex but rewarding topic linking geometry to observable effects. Social media trends often frame LIGO's detections as hearing the universe, a poetic yet accurate depiction, while ongoing pulsar timing arrays, like an ionograph, reporting potential low-frequency wave signals in 2023, add another layer by seeking waves from cosmic strings or early universe events that might hint at non-flat topologies. Historically, gravitational waves validate a century-old theory, echoing Michelson-Morley's 1887 experiment on light's constancy, and push technology to extremes. LIGO mirrors detect displacements smaller than a proton's width. Pause and consider this trending idea. Could a future wave detection reveal a cosmic curve or fold, rewriting our spatial story? Tying to planetary science facts, gravitational waves from early universe events inform inflation models, shaping conditions for galaxy formation where planets like Earth, orbiting a G-type star at 149.6 million kilometers, emerged. As we explore this cutting-edge field, let's marvel at how these faint ripples, born from cataclysmic events, offer a new lens on the universe's shape, inspiring global collaboration and curiosity. Next, let's delve into the trending concept of the observable universe versus the whole, a distinction critical to understanding why the shape debate remains open and frequently debated in 2023 cosmology webinars and Reddit's r/Ask Science community. The observable universe, a sphere roughly 93 billion light-years in diameter centered on Earth, is limited by the distance light has traveled since the Big Bang 13.8 billion years ago, expanded by cosmic stretching. Yet, the full universe likely extends far beyond, possibly infinitely, as suggested by inflation models positing a rapid early expansion by a factor of 10 to the power of 26 in less than 10 to the power of -32 seconds. Within our observable patch, CMB and galaxy surveys indicate flatness, but beyond the cosmic horizon, space could curve, loop, or adopt exotic topologies like a dodecahedral or toroidal form, undetectable unless light loops back within our view. An effect sought but not found in CMB pattern repetitions per 2023 studies. This discrepancy fuels trending discussions, amplified by popular science books like Katie Mack's The End of Everything, 2020, on whether our local flatness is a cosmic illusion, with simulations suggesting a closed universe might appear flat if its scale exceeds 1.2 times our horizon, per a 2019 Nature Astronomy paper. Educationally, this teaches the limits of empirical science. Our data is finite, bounded by light's travel, introducing concepts like the particle horizon, 46.5 billion light-years radius, and event horizon, beyond which we'll never see due to expansion, crucial for understanding relativity and observational bias. Social media often viralizes images of the cosmic sphere, sparking debates on infinity versus finitude, while missions like the European Space Agency's Euclid satellite, launched July 2023, map 3D galaxy distributions over a third of the sky to test if large-scale structure hints at unseen curvature. Historically, this mirrors Copernicus' 1543 shift from Earth-centric to heliocentric views, expanding our cosmic perspective, just as today's horizon challenges expand our grasp of all there is. Reflect on this hot topic. Does the idea of an unseeable beyond make the universe feel vaster or frustratingly out of reach? Linking to planetary science, the observable limit shapes exoplanet searches. Kepler and TESS missions, identifying over 5,000 exoplanets by 2023, probe only nearby stars within this bubble, a fraction of potential worlds. As we ponder this, let's recognize how the observable whole divide, trending in public and academic spheres, drives innovation in theoretical cosmology, pushing us to imagine shapes and structures beyond light's ancient reach, a testament to human curiosity's boundless scope. Lastly, let's tackle the trending intersection of quantum cosmology and the universe's shape, a speculative yet increasingly discussed field in 2023 conferences like the International Conference on Quantum Gravity and Popular Science Media, exploring if quantum effects at the Planck scale, 10 to the power of -35 meters, where spacetime may foam, could dictate geometry on cosmic scales. Quantum cosmology, blending quantum mechanics with general relativity, suggests the universe's birth involved quantum fluctuations during inflation, potentially imprinting non-classical shapes or topologies, as theorized in loop quantum gravity, LQG, where space is discrete, not continuous, challenging smooth curvature models. While no direct evidence exists, quantum gravity remains untested due to energy scales beyond current colliders like the LHC, operating at 13 TeV. Simulations and thought experiments, trending in journals like Physical Review Letters, propose that early quantum states could favor flatness via symmetry or create multi-connected spaces, detectable perhaps in CMB quantum noise or primordial gravitational waves. Targets for future detectors like the Cosmic Microwave Background Stage 4, CMBS4, project planned for late 2020s. Educationally, this introduces quantum field theory and uncertainty principles to students, showing how Heisenberg's limit, position and momentum can't be known simultaneously, might apply to space-time itself, a mind-bending extension of high school physics, while tying to string theory's extra dimensions, up to 11 in some models, that could fold into observable geometry. Social media, especially TikTok science explainers, often viralizes quantum foam visuals, sparking public fascination, while debates rage over LQG versus string theory's implications for flatness, with 2023 papers suggesting quantum bounce models, avoiding a Big Bang singularity, might imply a closed pre-expansion phase. Historically, this echoes early 20th century quantum pioneers like Bohr and Heisenberg, whose ideas reshaped microphysics, now scaling to cosmology. Pause on this trending query. Could quantum rules mean the universe's shape isn't fixed but probabilistic, fluctuating at its core? Linking to planetary science facts, quantum effects in the early universe set baryon-to-photon ratios, measured at 6.1 times 10 to the power of -10 via CMB, dictating matter formation for stars and planets like Earth, with its 71% ocean-covered surface. As we explore this frontier, let's marvel at how quantum cosmology, a hot topic in theoretical physics, bridges the smallest scales to the largest questions of shape, flat, curved, or stranger, reminding us that the universe's form might be written in a language of probability and uncertainty, awaiting our next leap in understanding to decode its deepest secrets.